Okay, I'm recording. Are you recording?
I'm not recording, but you're recording.
Okay, sounds good. Hello, Perry.
Hey, Carlos.
Welcome to the blockchain. No, not the blockchain journal club. Ozeki Journal Club.
Special
Much better.
blockchain edition, though.
We're back to the blockchain edition finally. I feel like
Yeah.
I'm forgetting all about it, but now that it's all the rage, of course, we're hopping back on the bandwagon.
In light of Ethereum exploding, actually.
It did explode, eh?
Yeah. Today we'll be talking a little bit about Ethereum.
Not ATH yet, though.
Really? Okay, I don't know.
No, it wasn't. I mean, I know the price is in Canadian. It was like 2,000 at one point. No?
Oh, yeah? Okay, I'm not sure.
Over 2,000. But yeah, okay, so that's cool, actually. We're doing an Ethereum, not paper, blog post.
Yep.
Exciting.
So it's our first stab at trying to understand the specifics, or at least some, I guess, some general specifics about how proof of stake works.
General specifics.
Some, I guess, generally how proof of stake works, and how can I say low level? Is low level the right word, or high level? I always forget.
Probably high level, no? Like we're not going in detail.
Yeah, so high level, how proof of stake works. This is a blog post by Johannes Hageman. I'm not sure. Hageman.
Hagendas. I tweeted at him. Hopefully he'll reply one day.
Yeah, maybe. But yeah, although there's Casper Ethereum in the title, I'm not sure how specifically this is linked to Ethereum, actually. I think this just gives some high-level features of how proof of stake works.
But he talks about the different proof of stake implementations, no?
Yeah, but I don't think he gets into the general specifics of them.
Oh, I see.
Yeah, so maybe we should just get started, right?
Yes. So you're leading this one.
I will lead. You will follow. So
did you read any other stuff besides this?
I did.
Okay.
I read also this blog post, which is on blockgeeks.com.
Okay.
Has similar information, a bit more detail, or general specifics. And then I read, some stuff about selfish mining. I also read this FAQ on the Ethereum Wiki, which gives a lot of detail. Like, this was just a bit too dense for me to take a stab at as a first go at really trying to understand proof of stake. I also looked at the /share protocol that we'll get into maybe.
Sweet.
So so basically what is proof of stake? It's just an alternative to consensus on blockchains. It's an alternative to proof of work, or POW. Okay, and basically right now, a lot of the major blockchains achieve consensus using proof of work. So these include Bitcoin, and at least at the time of this writing of this article, Ethereum as well. And just generally how proof of work works is miners get rewarded for validating transactions by solving cryptographic puzzles, or basically by hashing blocks until they get a value of the hash that's lower than some nonce. And by doing that, they get rewarded in Bitcoin, say, for the Bitcoin network, or Ethereum in the Ethereum network. Right. So that's how proof of work works. So you back up, you prove that transactions are valid by applying work to a system, to the system. Is your audio okay?
All good, yeah. Just thought there was someone at the door, but false alarm.
Okay.
I'm with you. I know how proof of work works. We wrote a paper about it.
Very sorry, sir. So that's how you mine blocks with proof of work, right? You apply some work to the network, and that demonstrates that you've checked transactions. And this work presumably costs you money through the energy and the computers you've bought to perform this work. So there's an incentive not to cheat, because if you cheat, you've lost a bunch of money in performing work on some invalid block.
And also, I think another aspect is that the work kind of accumulates, no? Like, doing work on top of, you work on top of work that's been done before. So reverting it means you have to revert the cumulative amount of work that's been done.
That's right. So at every stage of the network, I guess, or at every stage of the blockchain, there's somehow a guarantee that the work is, or how can I say, after every block that's added to the blockchain. So if you had a block n, if there's n plus 1, n plus 2, n plus 3, the number of blocks added subsequently to n reinforce how valid n is, because if n was invalid, then everyone that mined on top would also be invalid, and all that money or work would be lost.
Yeah. So
it's reinforcing, so every block that's added on top of a given block reinforces the validity of that block. Okay, and again, yeah, so that's a pro, I guess, of how a pro of proof of work. So problems of proof of work. According to this blog post, the biggest problem, I guess, or a big problem, is that it consumes a lot of electricity. So more than all of Ireland, for example, at the moment. And this just comes from the miners trying to solve these cryptographic problems, just hashing. Okay, and another problem, obviously, is because it costs so much money to mine, right? And your mining power depends on how many miners you can afford. There's a centralization of the mining power right now. So in this graph, you can see, I guess, that 24.8% of the mining comes from BTC.com, for example, and there are four, I guess even six entities that control over 7% of the mining power each on the network.
Over 70%.
Sorry?
Did you say 7% or 70%?
Each individually of these 8 control at least 7%.
Oh, okay, I see. Yeah.
I mean, the point I'm trying to make, or that this article is trying to make, is that there's only a handful of people actually mining, or entities actually mining. So although this claims to be a decentralized network, it's not fully decentralized because, most of the mining comes from only a handful or a limited number of participants. And that's similar for Ethereum, right? Where you have this pool over here that controls 27 or 28% almost of the mining power. So in the numbers, so in Bitcoin, they say we can see that only 4 big mining pools control over 50% of the whole hashing power. And for Ethereum, that's controlled by only 3. So in the context of a 51% attack, it seems that, if just 4 entities got together for Bitcoin, they could 51% attack the system. And for Ethereum, that's only 3. So it's a bit scary, Okay, so that comes in now. What comes in is proof of stake, which is an alternative to proof of work. So again, it's a consensus algorithm. So it has the same purpose as proof of work, to validate transactions and to avoid double spending, right? So yeah, we didn't mention it, but I guess double spending is a big reason why proof of work is important, right? If you want to double spend, you'd have to fork the network and perform the same amount of work that was already performed in the network to double spend your coins. And that costs you a lot of money. So there's an incentive to be honest, because you don't want to lose a bunch of money if your double spend fails. So now we want to replicate those features of proof of work using a different system that also maybe keeps the system from centralizing and that doesn't consume as much energy. That's the goal of proof of stake. Okay, so in proof of stake, as they describe in this paragraph, so there's no miners anymore. There's no one trying to solve these cryptographic problems, but they have people called validators now. And the validators vote on the next block. And there's one caveat or one important feature is that the weight of the vote, so the vote of every validator is weighted by how much stake they have in the network. Okay, and to become a validator, you have to send a special type of transaction. For Ethereum, this transaction would contain some ether, and that ether will be locked into the network. And every time you validate a block, you get rewarded in ether. Basically get rewarded in ether. Yeah, so that's the way this works, right? So instead of a miner pumping power or electricity into validating blocks, you have someone that's backing a block with money, basically, the ether they control.
The locking step, is that like a one-time thing? Like you do it so that you become a validator and then you can validate blocks? And every block you validate depends on how much you locked initially? Or is it like a per block thing? Like if I decide I want to validate on this block, I need to put in a deposit.
So I think this depends on the type of transaction that's implemented, but my naive guess is that you lock up, say, a fixed amount of ether.
Mhm.
So I guess let's say there's some threshold value that you lock up, or not a threshold value, but an amount you have to lock up to be a validator. So you lock that amount of ether. That ether now is locked for some period of time. And every time you lock up this fixed amount of ether, that gives you one chance out of all possible validators of being able to validate the next block.
Okay, sure. Yeah.
So probabilistically, you gain money proportional to the amount of ether you've locked up, basically.
Yes.
Right? So in the long time limit, if you control 1% of the ether locked up, you will get 1% of the rewards.
Okay.
Yeah. And then, okay, the author of this blog post goes into two major types of proof of stake, which I don't think he comes back to in the later part. So it's a bit, I think he just presents them. But there's the chain-based proof of stake and the BFT style proof of stake. So the chain-based one, there's a random validate. Well, the algorithm randomly selects a validator during each time step. So you have some period of time where validators are selected, and in that period of time, you can propose a block. Okay, and then the BFT style, or the Byzantine fault tolerance style, the validators are randomly chosen for each round. And then for each round, those validators agree if a given block is part of the chain or not.
So I don't think, sorry, I don't think the blog goes into this, but obviously the problem of randomly choosing something on the blockchain is not trivial, right?
Yeah, that's true. So from my understanding, the randomness, I'll get into it a bit later, but the randomness just comes from the hashes of previous blocks.
Yeah, but I guess it's deterministic, right? Anybody can know who the next validator is going to be given
or the next set of validators, yeah.
Given the current block, yes?
Yes, but I don't think this is an issue because your ether is locked, basically.
Okay.
So there's a fixed pool of validators possible.
Yeah.
You look at the hash, and it tells you who can validate the next block. You look at a hash, and it tells you which subset of those validators can validate the next block.
I guess you could, in theory, though, propose a block that's going to choose you as the validator, right?
Okay, yes, but again, it's probabilistic. So if I'm not mistaken, one example of proof of stake would work like there's some threshold value, like a nonce or something, some threshold value, and you multiply your stake by the time since the last block times the hash of the previous block.
Mm-hmm.
And if that's bigger than the threshold, you're allowed to propose a new block.
Okay.
Right. So yeah. There's extra things that come in, and the threshold can move, obviously. So making it maybe more difficult to be able to propose a first block that would have you as a potential validator for the next block.
Okay.
And there's still a competition, I guess, in some sense, right?
Yeah, and there's probably also like, there's a voting system, no, in the block, or is it really like, I guess whatever, there's probably many versions of this, right? But
yeah, but I think the validators, I think you can propose a block and then people vote if that block is okay or not, right?
Well, I think it's going to come in later, right, with like the delegated proof of stake.
Okay.
Like the sort of the one where everybody just votes on what the block should be, and then there's one where you vote on who's going to validate the block, right?
Mm-hmm.
And if if at the end of the day, one person basically decides on the block, then I'm wondering maybe some attack is that you make it so that you're the one that decides what the block is, and the block double spends or something like that.
But I think that the problem is you still cannot propose an invalid block.
Yeah.
Because validators have to vote. I mean, just adding new blocks to that would not work, would not happen, right?
Yeah, that's true.
So yeah. Anyways, there's some more details on this chain-based proof of stake and this BFT style in this Ethereum Wiki proof of stake FAQs. So it describes basically what we just said. So in this chain-based algorithm, there's some validators selected pseudo-randomly. And that validator has the right to create a single block. Yeah. And so over time, just like proof of work, this thing will converge to some into the longest chain, which is the valid history. The difference between chain-based though and this BFT style is that chain-based eventually converges to some history, whereas BFT style, at every block height, the validators have decided which is the valid block.
Mm-hmm.
So you don't. I mean, they talk about it here. Yeah. So here, note that blocks may still be chained together. The key difference is that consensus on a block can come within one block, and does not depend on the length of the size of the chain after it. Okay. So in this BFT style, the validators agree on the current version of the blockchain after every block.
Right.
Okay, these are just two flavors of proof of stake. Okay, so now this is the only mention, I think, of the Casper protocol in this blog post, even though it's in the title. But they're just describing here that right now there are two proposals, or main proposals, I guess, for the proof of stake to implement on Ethereum. And that's Vitalik's Casper, which is called the Casper FFG Friendly Finality Gadget. And Vlad's Casper, which is from this guy, Vlad Zamfir, which reminds me of someone, but I don't know who. But this Casper CVC, which is correct by construction, called Casper the Friendly Ghost. Okay, so I mean,
I think I know who it reminds you of.
Who?
I think there was this someone at Marinopolis, one of the teachers there had a name like that.
I'm feeling something like that. Yeah.
Yeah. All right. Well,
Can't
we'll
remember.
think of it.
But okay, so I think what's important to understand is that Vitalik's Casper is a hybrid between proof of work and proof of stake. So I think the way this works is that there's proof of work still implemented, but after every there's a fixed epoch time where it's, let's say, 300 blocks, and after every 300 blocks, validators vote if the history is valid, and that locks in the history for that after that epoch, or epic, or whatever we call it. And this one, I try to look it up a bit. It's pretty confusing to understand for me, actually. I think I need some more time to read about it. But these are the two main proposals. And I think right now they're implementing Vitalik's Casper. Okay, and then now we go into the pros of proof of stake. This quote over here, I see it in every article I read about proof of stake. So the cost profile of a repeated 51% attack in proof of stake is as if your ASIC farm burned down with each additional round. So yeah, okay. So this is a quote that I see everywhere. And I think the message you're trying to get across is, if you try to cheat in proof of stake, you can construct proof of stake so that if someone cheats, they not only lose their not only lose the reward that they would have got, they also lose all the resources they put into even being able to construct such a reward. So it's as if you not only lose the reward in proof of work, but also if you cheat, someone blows up your mining farm or something, you know? So you lose all the ASICs you just bought.
Mm-hmm.
Okay, so let's just get into it. I mean, they say it here, right? It means that proof of stake makes a 51% attack a lot more expensive. Because what happens is if you try to cheat, you also lose your stake.
Right.
You don't only lose the
Yeah.
rewards generated by the stake, you also lose the stake locked up.
Yeah. Yeah. I was reading somewhere else. I think maybe it was in the Ethereum Wiki. Maybe not. No, it was in an article I found. Like that a problem maybe with proof of stake is that the the cost to validating, or the cost to being malicious, is in terms of the cryptocurrency itself. So it's like kind of a circular system. Whereas in proof of work, you're actually putting in like a resource from outside into the system. And I don't know, like, if that rings a bell with you.
So I know one thing I read. So first of all, let me just say this statement here is a statement. I don't think there's an explanation behind it. I try to understand the explanation of it. We can get into that. I think the point you're making though is that in Bitcoin, say, I have to reward miners somehow with something that's valuable, right?
Yeah.
Like I have to give them more than what they put into the network, or equivalent to what they put into the network. Otherwise, they won't put anything into the network.
Yeah.
So the Bitcoin, say, has to be inflationary, right? Because I need to reward people with new stuff. Otherwise, they won't keep up they won't keep investing into the network.
Yeah.
With proof of stake, though, people invest Ethereum into the network, but maybe one thing I can do is burn some of the rewards, say, or reward the person for staking, but I can burn, say, some of the transaction fees.
Mm-hmm.
And in this sense, I can get a deflationary network even if I wanted.
Mm-hmm.
I don't know if you understand what I'm trying to say.
Sure. I mean, well, in Bitcoin, you have a hard cap on the mining, right?
Right.
At a certain point, you stop creating Bitcoin.
Yes, but I can never get into a system where I remove Bitcoin from the universe.
Mm-hmm.
I mean, I can if people lose it, but no one would mine if at the end of the mining I've removed Bitcoin, right?
Yeah. Yeah.
Ethereum allows you, though, because it's, well, not Ethereum, sorry, proof of stake. You can remove Ethereum or the token from the universe, because in reality, the person validating the network has not actually invested any money into validating.
Yeah.
His stake is locked up that he'll always get back, and the rest is just bonus, right?
Sure. Yeah, I guess the idea is that what you lose in Bitcoin is real external resources, right? If you're malicious. In a proof of stake system, you lose tokens that are valid only within that system, right?
Right. But is
So
that
in a
better?
sense, like it's maybe like zero cost in a sense, like there's no real sacrifice, right?
Is that true? But I mean, it depends if the tokens are valuable or not, right?
Yeah, I guess so. Then maybe what you're losing is like the potential to leverage it against some external resource.
Or the potential to even sell it for another resource, right?
Yeah, yeah. I'll have to look for that quote again.
Okay.
Maybe like when we do another episode on this.
Sure. Okay, so right now the pros of proof of stake, one is this burning down your ASIC farm, which is something that's not very clear from this sentence, but maybe we'll get into it a bit later. Another one is that proof of stake, they talk a lot about this economy of scale thing. So for Bitcoin, we have proof of work. It's much cheaper if I have $10 million to buy 10 million mining rigs than it is if I have $1 to buy one mining rig. Right? So I can scale how I purchase my mining power. You know, I can make, if I'm a huge company, I can make deals with the local, like here, Hydro-Quebec, say, to purchase large amounts of hydroelectricity at a lower price, making it much easier for me to accumulate a lot of the power or a lot of the work on the network, because I can scale my costs. So once you're very rich, or very established in the mining community, whatever, have a lot of miners already, have invested already a lot of money, it's easier for you to scale to get bigger. And it's much harder for someone that's very small to get to the level where you are.
And in proof of stake, is the reward like a linear relationship to what you invest?
So yeah, so proof of stake, alternatively, if you stake X amount of dollars, you get X amount of rewards, or Y amount of rewards.
Yeah.
Right? Because so I can't scale. If I have 10,000 Ether, I'm 10 times more likely to mine a block than the guy that has 10 Ether.
That's 1,000 Ether.
Yeah, if I said 10,000, I meant 1,000. And
okay.
if I have 10 times more Ether than someone, I make 10 times more than the person.
Sure. Okay, cool.
Whereas if in Bitcoin, if I have 10 times more money than someone, it's possible that I can multiply by 20 the amount of work I can produce on the network.
Yeah, for sure.
Because like you said before, it's an external thing I have to buy. There's a negotiation involved with other parties, all this stuff.
Yeah.
Okay. And then finally, this is what I was talking about before, but electricity. Okay, maybe we save the planet a bit by reducing the amount of electricity consumed.
Who cares?
Sure. And then this is the argument I was making before. Because we don't need, there's no real cost to staking. It's just the tokens themselves. I can reduce the mining rewards. I don't have to give mining rewards that are big enough, as big as in Bitcoin, where I have to compensate the miner for spending all money on electricity, and I can have deflation, say, in some limit. I'm not sure if that's feasible or practical, but I guess in some limit, you can have a deflationary currency.
I guess we'll get into it, but what happens? How do you lose your stake? You know, like in what situations do you?
Yeah. So
get there?
The short answer is if you act maliciously, basically.
Yeah.
But I'll get to how that happens and why that works in the next section.
Sweet.
Actually.
Excellent.
And it's not covered in this article, but I think I've understood a bit how it works. Okay, so the cons of proof of stake. So the major con that I found with proof of stake is this nothing at stake problem. And this nothing at stake problem is also, it's like in 20 years, if proof of stake is the only thing, it'll be called the new 51% attack or something. You know, it's like everyone will quote this as the problem, the main problem with this. And what this means, this nothing at stake problem, what it is that every time the blockchain forks, if I have just some pure proof of stake where I just validate a block and put it on the blockchain, there's no incentive to pick one of these forks to mine on. Right? So let's say I get rewarded X Ether for adding a block to the blockchain. It costs me nothing in terms of electricity or external resources. So I might as well just add a block to this chain and this chain. And if this chain wins out, I'll get my reward here. And if this chain works out, I'll get my reward here. Right? So there's nothing keeping this blockchain from splitting. Well, once a fork happens, there's nothing from keeping anyone from closing or abandoning one of the forks.
Whereas in proof of stake, you have to pick one because you want to take a mined on top of, right?
In proof of work, you have to pick one because
proof of work, I meant.
Because proof of work, you have to pick one because there's a resource to add. So adding a block to this chain and this chain costs you twice as much money.
Yeah.
Whereas in proof of stake, it costs me the same amount of money to add to here and here. I have locked Ether here and I have locked Ether here. Right? So I'm a validator on this chain, and it costs me $0 extra dollars to add it to this chain and this chain. So I might as well just do it, right? And see which one wins in the long run.
Yes.
And this explanation I found a bit confusing, but the gist of why this causes a problem is that imagine now there's a fork in this network, and 99% of the validators just keep adding to both of these forks, right?
Like so this fork would just keep growing, is what you're saying? Like
yes, exactly.
And then at a certain time point, you're the one that's trying to decide where to mine on top of.
Well, every time it's my turn to decide, I'm just going to put a block on both.
Yeah.
Because in case one of these chains wins, I'll get rewarded on that chain. If I pick one, and the other one wins, I'll lose money.
Yeah.
But now this new attack that can happen, right? Imagine 99% of the people act in this logical way where they'll just mine on both of these forks.
Mhm.
And this 1% guy here decides to spend money on this block, in this block here. Or say in this block here, in this lower block. So he sends a transaction. Alice sends a transaction to Bob in this lower fork here.
Mhm.
And then adds his 1% stake to adding blocks only to this part of only to this chain.
Mhm.
That'll cause a double spend because this chain will grow longer than this chain because his 100% is mining on this chain, but only 99% on this chain. And the transaction Alice just sent on this fork will be lost.
Yeah.
So this kind of system allows you to double spend, right? Quite easily, actually.
But isn't there like again, sort of a number of blocks to wait before you approve a transaction here?
Yeah, but if I'm just acting in the terms of money, like just trying to make the most money,
Mhm.
these chains will
Yeah.
grow forever at an equivalent rate. Because every time a block comes up, every time a validator it's someone's turn to validate, they'll just add a block on both chains in case one wins.
Sure.
But now if I add 1% to tip the scales, that the chain I've added this 1% to will start beating out this chain, and people will stop mining on this chain.
Yes.
So all I have to do is spend money on this fork,
Mhm.
and then mine on top of the other one.
Yeah.
Losing the transaction on this fork.
Sure. Yeah.
So I can double spend like that.
I got it.
Right? And this is a problem, obviously.
Sorry, this like 99%, 1% thing, that represents like
Voting power, if you want.
the voting power of the network is, but 99% of the network is on this split, right?
So this 99% means that 99% of the vote mines on both chains.
Yes.
I'm the attacker. I decide to not vote until I spend on one of the chains, and then I vote for the opposite chain.
So this means like this 1% means you have a 1% chance of picking the next block?
Yes, exactly.
Yeah. Okay.
Right. So I control 1% of the locked ether.
Yeah.
So I can send that ether away here, and then mine on this chain, and then that grows.
Yes. And is there any like way of going further back? Like if I wanted to do this on a older transaction than whatever the current block is.
Yeah, so I think that's what this long range attack is.
Ah, okay.
Yeah, so yeah. But the idea of the way to prevent this, or a proposed idea to prevent this, is something called this slasher. And what this does is, okay, yes, this basically penalizes validators if they simultaneously create blocks on multiple chains.
Mhm.
And how does that work? That's just some words, but how does that work? The idea is the validators for a given block are determined sometime in the past. So at every block height, the validator for that block height is determined at like 2,000 blocks ago.
Okay.
Okay, so it's yeah, so Slasher uses proof of stake 2,000 blocks ago.
Okay.
And it's like this is like some sort of like a ratting up people out. If it so every block basically you know who can validate.
In 2,000 blocks from now.
Yeah, so at every height,
yeah,
you know who the possible validators are because you know the block 2,000 blocks ago.
Wait, no. Sorry, the way I was thinking of it is the current block tells you who's going to be the validator 2,000 blocks from now.
Yes. So
or it's the other way around.
No, it's the same. So right now, the block right now is that the validators were determined 2,000 blocks ago.
Okay, sure.
Right?
Yeah.
So everyone knows who can validate the next block on the blockchain.
Yeah.
And then basically, if you find someone that added blocks to two different forks, you can sign a special transaction specifying their block. And then they lose all their stake and you gain 33% of it.
Wow.
So it incentivizes people to catch people from cheating, to catch people cheating, basically.
It's not very elegant.
Really?
I don't know.
I mean, the problem with Bitcoin is the forks don't know about each other, right?
Yeah, that's what I was thinking, right? And it's kind of a nice feature.
Well, I think
they don't have to know about each other.
Sure, but now you need them to know about each other. Otherwise, you can do things like this, right?
Yeah.
So I think when they say this quote that is ubiquitous in this in all this literature,
yeah,
what it means is that if someone catches you cheating, you just lost all your stake.
Yeah. Is there an incentive for people to do this ratting out?
Yeah, they get 33% of the stake, I think.
Okay.
Something like that.
How do I feel about this? I'm not sure I feel good about this.
Yeah, and sends the so you see here.
Mm-hmm. The cheater.
It destroys the reward for the signature and sends 33% of the to the user that ratted the cheater out. Okay.
But it's also like.
Sorry, I said stake. It might be rewards actually. That 33% of the rewards gets sent to the.
Okay.
To the ratter.
So you don't like become rich or anything.
Well, I guess it depends.
I guess it feels kind of funny. Isn't it like free to fork the chain though?
It's free to fork, but it's not free in this system. I guess it's not free to add 2 blocks to 2 different forks at the same height.
Yeah. Yeah.
It's not free to create a fork by yourself. So, by the way, I should mention all this is done for the same height block.
Mm-hmm.
So it's as if I create a fork, that's cheating, right? If I put a block here and here, that's cheating. And then if someone puts 2 blocks on my thing, that's also cheating. So all those people get punished, is the point.
Yeah. Right. Okay, so it's not punishing this like 1% attack, it's punishing creating this structure, right? Of sort of double posting your blocks.
But that prevents the 1% attack because now forks don't happen.
Yeah. Huh. I'm going to go ahead and say that's a bit clunky.
So sorry, forks can still happen because 2 different people can propose different blocks?
At the same time, yeah.
Yes, but one miner cannot, or one validator cannot propose 2 different blocks.
Yeah. Yeah, I guess I just find it funny that like the network has to be paying attention to all forks, right? But I guess they don't really happen anymore unless there's sort of this like coincidence happening, right?
I mean,
that 2 blocks come out at the same time.
Sure, that can happen, I guess. And I think that's natural.
Yeah.
But what shouldn't happen is the next guy mining on, like the next validator should pick which chain is valid, right?
Mm-hmm.
You don't want 2 forks to extend forever.
Yeah, I see. So then how do you do a hard fork? Like let's say you want Ethereum Cash and Ethereum Classic.
So I think there's some other stuff going on here where they say that they don't. Okay, yeah. So the question is, how do you do a hard fork? You can still do a hard fork, right?
You just have to pick one every time you make a new block.
But if I'm a validator, I can't put 2 blocks on the 2 different the 2 blocks.
Okay. Yeah, I see.
So I can pick to do a hard fork and extend my chain in this direction.
Mm-hmm.
But I can't pick to extend my chain in this direction, but at the same time put my validating power behind both chains.
Yes. Okay. Got it.
For every block.
Mm-hmm. Okay. That makes sense.
Yeah. Okay, and then this long range attack, which is okay, yes, this is something else that if it basically costs you nothing to add blocks, you just need to stake. Like you said before, what if I go down 10,000 blocks before and just fork the chain and just keep validating my own stuff, and just keep adding blocks?
Well, you can't because you have to get chosen to validate, no?
Yeah, but that chosen time period, that period, I gotta get chosen, but that depends, say, on a timestamp.
Okay.
If I wait long enough, say, I will be the validator if no one has validated yet.
Yeah.
So there's an issue potentially with that happening, right? And one possible way to fix that is to use timestamps. So basically, that the protocol would ignore forks that happened too far ago in the past. So let's say every block has to include a timestamp, and if the timestamp is too different from the block that you're forking from, say, maybe that gets ignored.
Okay.
I don't know too much about this, by the way. I'm just reading what's written here.
Yeah. Okay.
Okay, and then this is the final section before the conclusion, but basically, besides proof of stake, there's something called delegated proof of stake. And that's implemented by, for example, Lisk, EOS, and Steam. It was developed by this guy, Daniel Larimer, who was at BitShares and I guess, yeah, and at EOS. And this is like, if you want, proof of stake is like this picture on the left, where everyone has a chance to vote on which block is valid, if they have stake in the network. On the other hand, delegated proof of stake, it's people vote for a representative that can then has the power to validate blocks. So it's like creating the staking pool. Well, I guess somehow staking pool, where you just put your stake behind a representative that'll be responsible for validating the transactions. Okay, so that's the gist of it. But again, okay, this is a problem with centralization, right? Because you're giving the power to a select few individuals that have the power to validate transactions.
But you can control it, I guess, right?
Yeah, I guess
really control in Bitcoin what's the centralization rate.
Yeah, that's true. So you're right, because I guess all these people can just change their vote if they want.
Yeah. Or I guess like in the blockchain itself, it says how many like representatives there can be, no? Like you just pick how many, like in theory, you could have every member of the network being a validator, right?
That's just proof of stake. Right? That's just the regular thing, right?
Yeah, for sure. But you can go in between as much as you want, right?
Yeah, but
it's just a choice.
But I feel like if you implement proof of stake, you can always go in between, right? Because you can just give your stake to some person.
Yeah, for sure.
Like if you trust them enough, I guess you can just give it to them. Anyways, I guess maybe this is easier to implement because there's a list of validators at every block, but this is maybe better or more general.
Yeah.
Generally specific. Okay, yeah. So that's about it. That's the main gist. This is like some overview of how proof of stake works. We didn't get into details about how Casper works, and in fact, right now I'm not sure about the properties or the specific properties of this Casper protocol. But yeah, those are the main features of proof of stake.
Very nice. We'll do another episode on it for sure.
Yeah. So basically what happens is you can still prevent. So just an overview. You've somehow replaced this 51% attack, this 51% hashing power attack, say, with this nothing at stake problem. But there's a proposal to eliminate it using this slasher protocol where you remove, where some cheaters would lose their stake. But yeah,
I guess there's still some sort of 51% attack, right? Because it's just that instead of 51% of hash rate, you have to have a certain percentage of the stake, right?
Yeah, that's true. So if you control 51% of ether, say,
but it's not always that. It's not always 51%, no? I think it depends. Remember when we spoke with Jacob? I don't know. His blockchain was 33% attack.
Okay, I guess. Sorry, what I meant was if you control 51% of a minimal condition is if you control 51%, or a sufficient condition is if you can control 51% of the total staked ether. Right, you can probably fork this network very easily and double spend. Yeah,
I guess you can approve your own transaction, your own malicious blocks, right?
So you spend on this block, say, and then just eventually be able to fork it And then the chances are you'll create the next block before this block gets created, right? The next block gets created.
Mm-hmm. I see. And there's no, I guess maybe this is the launch attack, because usually in Bitcoin you go around that by waiting 6 blocks. Before,
so here too, I think you can wait 6 blocks. I mean, I'm sure there's a certain amount of time you can wait. I mean, now they're introducing things like timestamps, right?
Yeah, that's it.
So it might be that, that gives you a time window for which you can attack the network.
Mm-hmm.
Because maybe after that timestamp or after a certain time, you cannot fork anymore at a certain block height.
Okay. Yeah. So let me try to recap. I guess in the simplest case, you participate in the network by locking up a certain amount of crypto. That gives you a probability of being the person that chooses the next block.
Yeah.
Right. And then if you choose a valid next block, you get a reward. If you somehow cheat, you lose your stake. Right. One of the ways you can lose your stake is by trying this nothing at stake attack. Right.
I don't know if it's an attack there, but it's at least a problem.
Yeah.
But yeah, so by double spending, say, or forking the blockchain intentionally, you can lose your stake.
Yeah, I guess the difference with proof of work, maybe I'm not familiar enough here yet, but is that there's like these rules on top of the blockchain that are like explicitly stated and get explicitly like enforced. Whereas
in proof of stake or in proof of work?
in proof of stake, in proof of stake. In proof of work, all that happens is the network doesn't mine on top of your block, right? And it's sort of a self-contained incentive.
Mm-hmm.
Here you're like waiting for someone to explicitly punish you if you do something wrong, right?
But it's the same as I think it's the same as someone not mining on top of it. It's equivalent, I guess.
Yeah, I agree it's equivalent, but I guess the way it's enforced is a bit different, right?
Sure, but I think you have to enforce it that way, right? Mm-hmm. And the reason is because there's no external, like you said before, there's no external resources you're burning.
Mm-hmm.
Because proof of work forces you to burn external resources, not getting a block that you worked for is already a punishment.
Yeah, exactly.
That's the point, I guess.
Yeah, that makes sense. Cool. And so maybe I'm curious about like the theoretical limitations or properties of proof of stake. I think there's some papers on that, but I mean, why isn't everyone just using proof of stake, right? Like, I wonder what are the downsides.
I think a lot of it is like things like this, right?
That seems not worse than a proof of than a 51% attack. And
by the way, maybe not, but this slasher thing I just talked about, I think is one proposal to get rid of this. There's probably others. I mean, in fact, there are for sure others.
Okay.
But there's probably a lot of work being done on this, right? To figure out the best way to prevent things like this from happening. And this, I guess, list long-range attacks. I just don't know enough about them now. And maybe I messed something up also discussing this with you. So maybe someone can comment on the video informing us of any errors we've made. Yeah. One of our 25 subscribers, perhaps.
Exciting. Yeah, no, that was really cool. I think I learned quite a bit. I'm down to do another paper on proof of stake, or maybe something more like, just like more generally specific, now that we have some basics.
And some terminology.
Yeah. Cool. We'll keep looking.
Yep.
Very nice.
So that was a quick little episode, and I guess more to come.
Excellent. We have some exciting next episodes coming up, don't we?
Absolutely.
Very nice. Well, thank you, Perry.
Thank you, Carlos. And I guess I'll see you next time.
See you next time. Ciao.
Bye.